Good morning, students. This is lecture number 14 on ray optics. Our next topic is astronomical telescope. This is the last optical instrument of this chapter. Okay, and after that, we have one more topic, that is reflecting telescope. Okay, and advantages of reflecting telescope over refracting telescope. Okay. So these are the remaining topics of this chapter. Okay, so we are going to discuss astronomical telescope. Here we have ray diagram of astronomical telescope. Okay, so what is the astronomical telescope? Astronomical telescope is also called the refracting telescope. Okay, an astronomical telescope is an optical instrument which is used for observing distinct images of heavenly bodies. Okay, what are the heavenly bodies? For example, stars, planets, etc., when the final image is formed at infinity. Okay, so what is the astronomical telescope? An astronomical telescope is an optical instrument which is used for observing distinct images of heavenly bodies like stars, planets, etc., when the final image is formed at infinity. Okay, so this is the ray diagram when the final image formed is at infinity. Okay, so as you can see that in the astronomical telescope, it has coaxially two convex lenses coaxially separated by some distance. Okay, separated by some distance. The lens towards the object is called objective lens and has much large aperture. Okay, then the eyepiece of the lens towards the eye. Okay, as you can see in the figure, this will be your eyepiece lens, this is your objective lens. Okay, what is the working? Light from the distant object enters the objective lens and real image is formed at second focal point of objective lens. Okay, so this will be your objective lens. Light rays coming from the distance object enters to the objective lens and real image is formed at the second focal point of the objective lens. The eyepiece lens magnifies this image and producing final inverted image. Okay, is at infinity. Okay, so this will be your image which is found by the objective lens at a second focal point of the objective lens. Okay, and the eyepiece lens magnifies this image. Okay, and producing a final inverted image at infinity. Okay, so this is the explanation of your ray diagram. Okay, now come to the case when the image is formed at infinity. Okay, so we have angular magnification. Angular magnification is given by beta upon alpha. Since beta and alpha are very small angles, then we can write beta is approximately equals to 10 beta and alpha is approximately equals to 10 alpha. Now we have to find the value of 10 beta and 10 alpha from our ray diagram. Okay, so after putting beta equals to 10 beta and alpha equals to 10 beta, we have m equals to 10 beta upon 10 alpha. This will be your angular magnification. Okay, which is equation number 1. Now come to the ray diagram. We have to find the value of 10 alpha. Okay, so this will be your angle 10 alpha. So in this particular triangle, we can find the value of 10 alpha. So what is the value of 10 alpha? That is perpendicular upon base. Okay, so the value of your perpendicular will be I and the value of this base will be f naught. Okay, So tan alpha equals to I upon f naught. Okay, tan alpha equals to I upon f naught. Okay, this is not I. Okay, just correct it. This is I only, and this is your f naught. Okay, now again come to the ray diagram. Here we have one more triangle. Okay, this making an angle beta with your optical center of eyepiece lens. So from here we can calculate the value of tan beta. So tan beta equals to perpendicular upon base. So this will be your perpendicular base. Okay, so the value of base is fe and the value of your perpendicular is again I. Okay, so tan beta equals to I upon minus fe. Why I take minus fe? Okay, because it is in opposite direction of the incident ray. Okay, capital I is the image found by the objective. Okay, f naught and fe are the focal lengths of objective lens and eyepiece lens respectively. Now substitute the value of alpha and beta, tan alpha and tan beta in equation number 1. We get m equals to minus I upon fe divided by I upon f naught. So finally m equals to minus f naught upon fe. This is the angular magnification when the image is formed at infinity. Okay, now we have case number 2, when the final image is formed at near point. Okay, when the final image is formed at near point, this will be your near point. Okay, so as you can see that this is your image. The light from distance object enters objective lens and real image is formed at the near point. Okay, and eyepiece lens magnifies this image again and producing a final image which is not inverted. Okay, so this will be your object distance. This is working as a virtual object for this eyepiece lens. So this is your object distance, this is your image distance. Okay, remaining things are same. Now again your angular magnification, m equals to beta upon alpha. So m equals to tan beta upon tan alpha, as beta and alpha are very small angles. Okay, now we have to calculate the value of tan beta and tan alpha. So what is the value of tan beta? So from this diagram, from here we can calculate the value of tan beta, and from here, from this triangle, we can calculate the value of tan alpha. So what is the value of tan beta? Perpendicular upon base. So what is your perpendicular? A dash b dash. This a dash b dash is your perpendicular, and this your c2 b dash. Okay, c2 b dash is your base. Again in this triangle, this will be your perpendicular a dash b dash, and this will be your base, that is c2 b dash. Okay, so here we have tan beta equals to a dash b dash upon c2 b dash, and tan alpha equals to a dash b dash upon c1 b dash. On now putting the value in the formula of angular magnification, so m equals to a dash b dash upon c2 b dash upon a dash b dash upon c1 b dash. Okay, this a dash b dash and a dash b dash will be cancel out each other. So we have m equals to c1 b dash divided by c2 b dash. Okay, now what is the value of c1 b dash? This will be your c1 b dash. C1 b dash, the value is f naught. Okay, c2 b dash is nothing but your object distance, that is ue, and again put the value of these two in our equation. So we get m equals to f naught upon minus ue. I think it is clear why I took here minus ue. Okay, according to the rules of image formation. Okay, by lens formula we have 1 minus v minus 1 upon v minus 1 upon u equals to 1 upon f. Okay, v is your image distance, u is your object distance, f is your focal length. Okay, So for the eyepiece lens, we have to calculate here for the eyepiece lens. Okay, so what is V? V is nothing but your D. Okay, U is nothing but is your UE, and F is FE. So for eyepiece lens, minus 1 upon minus D minus 1 upon minus UE equals to 1 upon FE. Okay, now 1 upon U equals to 1 upon FE plus 1 upon D on further solving that particular step. If I take 1 upon Fe as common, so 1 upon U equals to 1 upon Fe plus 1 upon Fe into 1 plus Fe upon D. Putting the value of this 1 upon UE in equation 1, we have M equals to minus FO F naught upon Fe into 1 plus Fe upon D. So this is the angular magnification of astronomical telescope when the image is formed at near point. Okay, now come to the next one. That is reflecting telescope. Okay, the your last optical instrument. Okay, so reflecting telescope. What is the reflecting telescope? First of all, it is also known as a Cassegrain telescope. Okay, which was designed by Cassegrain. Okay, reflecting telescope is an important over refracting or astronomical telescope. Okay, is an improvement. It is an improvement over refracting or astronomical telescope. Okay, so to obtain a bright image of a distant star by refracting telescope, it is essential to have an object of large aperture so that it may collect more light coming from the object. But to deal with such a big lens is problem in terms of using and making, and it is costly too. Okay, so the same bright image of a distance object can be obtained by using a concave mirror of large aperture in place of objective lens. Okay, so as you can see in the figure, okay, it is a improvement over refracting or astronomical telescope. Okay, so if for making this type of telescopes, if is such a big problem. Okay, so that's why we have reflecting telescope. Okay, so the reflecting telescope consists of, as you can see in the figure, reflecting telescope consists of concave mirror of a large aperture. Okay, concave mirror, here you can see that concave mirror of large aperture and large focal length. Okay, a convex mirror is placed between the concave mirror and its focus. Okay, so here we have objective mirror, here we have one concave mirror which is placed is at its focus. Okay, a concave mirror is placed between the convex mirror is placed between the concave mirror and its focus. A small convex lens works, a small convex lens, here you can see a small convex lens works as eyepiece. Okay, this is small convex lens works as eyepiece. In the reflecting telescope, parallel rays from a distant object are intercepted. Okay, from a distance object are intercepted and focused by reflecting concave mirror rather than a reflecting lens. Okay, focused by a reflecting concave mirror rather than a reflecting lens. Okay, one popular configuration of mirror and eyepiece is called Newtonian reflecting type telescope. Okay, one popular configuration of mirror and eyepiece is called Newtonian reflecting type telescope, named after its designer Newton. Okay, so here we have a Newtonian type reflecting telescope. Okay, Newtonian reflecting type telescope. The parallel beam of light coming from the distant object is reflected to concave parabolic mirror. Here we have, this one is your parabolic mirror, this one is your plane mirror. Okay, so the parallel beam of light coming from the distant object is reflected to concave parabolic mirror, that is your M1. Okay, reflecting from this particular mirror M1 on the plane mirror M2. Okay, so plane mirror M2, the plane mirror M2 is inclined at an angle at 45 degrees. This particular plane mirror inclined at an angle of 45 degree to the axis of the mirror. Okay, the plane mirror reflects the beam and a real image is formed in front of eyepiece lens. Okay, in front of eyepiece lens, the eyepiece acts as a magnifier, and the final magnified image of the distant object can be observed from the eye. Okay, the plane mirror reflects the beam and a real image is formed in front of eyepiece. The eyepiece acts as a magnifier, and the final magnified image of distant object can be observed by the eye. Okay, okay students, so this is the end of your chapter. This one is your last optical this was your last optical instrument. Okay, we have one more topic, that's it, that is advantages of reflecting telescope over refracting telescope. So I discuss this particular topic orally. Okay, so listen carefully. For astronomical telescope, the mirror affords several advantages over the objective lens. Okay, for astronomical telescope, the mirror affords several advantages over the objective lens. A mirror is easier to produce with a larger diameter so that it can intercept rays crossing a larger area and direct them to the eyepiece. Okay, what I say? A mirror is easier to produce with a larger diameter so that it can intercept rays crossing a larger area and direct them to the eyepiece. Okay, the mirror can be made parabolic to reduce spherical aberration. Okay, aberration is further reduced because passage through one layer of glass is eliminated. Okay, one layer of glass, that is your the objective lens, is eliminated. Okay, okay, so this is the end of this particular lecture and also the end of our chapter, our unit, that is ray optics and optical instruments. Okay, if you have any confusion or any doubt, please ask me in our WhatsApp group. Okay, or you can ask in the comment box also. Okay, thank you so much.